Welcome to today's webinar, Grounding for Renewables, Grounding Between Interconnected Grounding System in Solar and Wind Renewable Generation Projects. We'll get started here in just a couple minutes, let a few more people filter in. All right, so out of respect for everyone's time, and plus I know that our presenters, Gerry and Rich, are going to use most of the hour here, we'll go ahead and get started. So again, I wanted to give a very warm welcome and thank everybody so much for taking the time to join us today. So our webinar is titled Grounding for Renewables, Grounding Between Interconnected Grounding Systems in Solar and Wind Renewable Generation Projects. My name is Lake Lund, and I'm a Business Development Manager here at Commonwealth. I'm joining you from Boston today, but typically I'm in Dallas. It's been really good to be in Boston and kind of enjoy another springtime. And Gerry, if you don't mind flipping over to the next slide, I think that'd be perfect. There we go. Thank you for that. So today's session is designed for professionals across the engineering industry. So whether you're just beginning your career or looking to take the next step in your career journey, today's session is going to be a perfect fit for you. So just a little bit about Commonwealth Associates. So we are headquartered and based in Jackson, Michigan, and we have 7 office locations across the United States. I like to say that we are a soup to nuts engineering and design firm with over 37 years of experience in the power industry, and we provide expert engineering and consulting services for the energy market. Our expertise encompasses renewable energy, power delivery, power generation, and system studies and consulting. And I'd invite everybody to take a look at our updated website, cai-engr.com. It's very fantastic, and we post a lot of different projects we've done on there. It's a great read. So today's webinar will make everybody eligible to receive a PDH certificate. So you can see my email on there. You can also email marketing@cai-engr to receive that certificate. So for the Q&A, we welcome everybody to please ask questions throughout the webinar. We will get to those at the very end of the presentation if we have enough time. But we want to try to make this as interactive as possible. So feel free to give a thumbs up. We're going to ask a couple poll questions here in a minute, and we want everybody to take a chance and make sure that their voices are being heard, because we want to make sure this presentation is curtailed more so to the audience that's actually here and listening. And of course, the recording of this webinar and all of our prior webinars are found on our YouTube channel. The QR code we've placed on this page here can be scanned with your smartphone, and it'll take you right to the YouTube channel, and we'd love if you guys would subscribe. And the next webinar we're going to have is going to be in August. We'll be sending out some more details on that soon. And as I mentioned, we have a couple of different questions here that we are going to ask the audience. And Gerry, if you want to flip to the next slide, and I'll get those questions queued up here for everybody to answer. It should pop up on your screen as well. Just one second. Okay, everybody should have received the first question. How familiar are you with IEEE 80? Take a second to get that answered. Then we have one other question here. Okay. Which best describes your experience with grounding design for collector stations or renewable energy plants, so solar wind opportunities? All right, sounds good. It looks like we have a very diverse mix here with us today, so that's fantastic. We definitely love to see that. Well, perfect. Well, without further ado, I will turn it over to our presenters, and we'll get to it. Gerry, Rich, feel free to hop to the next slide, and you guys take it over from here.
Hello, Lake. Thank you. My name is Gerry Callison, and I am a substation studies engineer with Commonwealth Associates here in Jackson, Michigan. And I'm going to talk a little bit about some background in grounding and I'll let my colleague Rich Keil introduce himself.
Hi, I'm Rich Keil. I've been in the utility industry for a long time. I spent 35 years almost at Dayton Power and Light as a design engineer, and I've been with Commonwealth almost 24 years. And I've been a member of the working group responsible for Guide 80 since 1976, and I've been chairman since 1986. So that's my background.
Thanks, Rich. Before Rich dives into some of the innovative solutions that he's going to introduce, I'll provide the group with some background on grounding to help people understand what it is that Rich is going to introduce to us. So with that, what on earth is a ground grid in the first place? You know, a ground grid is horizontal conductor, a combination of horizontal conductors and vertical ground rods that are buried in a pattern across a specified area below a substation. Now, why on earth are we putting this copper, which is prone to theft, underneath the substation to begin with? Well, basically a ground grid does two large functions. During steady state operation, it provides a source of ground. Is that, you know, your dead tank circuit breakers are dead tanks because they are grounded. Their grounding is connected through leads to the ground grid, to the station's ground grid, and that provides a source of provides grounding during normal operations. During fault operations where you have a ground fault, the ground grid provides a interface between the grounding system and the soil that current enters and then travels through the soil back to its source, remote earth. And basically, a ground grid ensures when this current during faulted conditions is entering the grid to soil interface that touch voltages and step voltages throughout the station are maintained below safe thresholds. And we'll talk a little bit about what touch and step voltages are in a few slides. So what is it that impacts the design of a ground grid? Well, one of the significant factors impacting the design of a ground grid is the surface area that the ground grid is covering. What is the surface area that the footprint is covering? The second significant factor is the soil that it's buried in. What is the resistivity of the soil that the ground grid is buried in? You know, when we're designing a ground system, we'll create a soil model of different resistivities at different depths, and we'll do that based on measurements that are taken in the field, usually using the Wenner 4-pin method. So that's modeling soil, which is very important to the grid design. Another factor is how much fault current can the system provide at that site? You know, is based on where it's connected in the power system, how much ground fault current is that power system capable of delivering to the point where the ground grid is located. Another important factor in the design of ground grid is split factor. And I'll show you some pictures in a few slides of what split factor is. But basically, split factor is good as a factor that's going to be determined based on the resistance of the grid and the amount of paths that are line paths, you know, shield wires and transmission towers, distribution neutrals and distribution towers, the amount of paths that are leaving the station, counterpoise towers, things like that. So with that, let's talk a little bit about ground potential rise. It's a term that is going to be tossed around quite a bit during this presentation. Well, you know, what is ground potential rise? Well, ground potential rise is the maximum electrical potential that a ground electrode may attain relative to a distant grounding point assumed to be at the potential of remote Earth. This voltage, GPR, is equal to the maximum grid current times the grid resistance. Okay, that was a standard definition that I just read to you. Let's look at a picture and see what actually ground potential rise is. Here we see a picture of a very simple grounding system. We see a remote source providing ground current through a transmission line into a station bus that has a single line to ground fault, providing fault current into a ground grid, which is buried in the soil. And the soil is then, this ground current is then leaving the ground grid through the grid to soil interface and traveling through the soil back to remote Earth. Now, the ground grid there's a resistance between this ground grid and remote Earth. And that's the resistance of the ground grid. And and as this ground current leaves the ground grid through the grid to soil interface and goes back to remote Earth through that resistance, well, resistance times current is equal to voltage. And so this ground grid will rise relative to remote Earth. And that rise relative to remote Earth is the ground potential rise. So that is a picture of a grounding system with ground potential rise. Now, talk a little bit about ground potential rise. There are some faults in a station that are not going to produce significant ground potential rise, and therefore we don't really look at them when we're studying grounding system design. A lot of those faults are basically, a lot of times occur on a distribution bus in a substation, and that's because the distribution bus is fed from a grounded Y winding of a transformer. So whenever we have current that's source is coming from the neutral through a grounded Y, we don't consider that in grounding design because it doesn't affect GPR. And the reason for that is that it does not enter the grid to soil interface. Here we see this ground fault. We see a single line to ground fault on a phase where our fault current goes into the ground grid. Now this current single line to ground fault is all coming from the neutral of this transformer. So it's coming from the neutral through this phase winding to the faulted phase back into the ground grid. And it wants to get back to its source. But instead of going through the grid to soil interface and creating a V equals IR ground potential rise, it stays in the ground grid largely and goes through the ground grid from the fault location to the location where this transformer neutral is grounded. And then it goes through those ground leads into the transformer neutral back to the fault. So basically, it is a circulating current, and we do not consider this for grounding, aside from some very specialized, a few very specialized situations. So, well, I've talked a lot about, I've thrown around the terms touch and step voltage, and it's important to understand what these really are when we're understanding grounding. So we'll look at the standard definitions of what they are. Touch potential is the difference between the ground potential rise, the GPR, and the surface potential at the point where a person could be standing while at the same time having a hand in contact with a grounded structure. A step potential is the difference in surface potential that could be experienced by a person bridging a distance of 1 meter with the feet without contacting any grounded object. Okay, so a picture is going to be a lot better and very helpful in understanding what these touch and step potential terms actually are. So let's start with a step potential. That's a relatively simple one to understand. What is the difference between points on Earth that are on the surface that are 1 meter apart that a person could be bridging with his or her feet? You know, is that we assume that there's 1 meter between the feet, which is a little larger than what most people can step, but that's a conservative assumption. So what is the potential difference between a person's feet? That is a step potential. A touch potential, however, is a little bit more complicated, but very critical. Is that as current is leaving the ground grid through that grid to soil interface in its path back to its source, creating that ground potential rise, the potential of the ground grid is rising. Now, if you have a grounded structure like we see, maybe something like a light pole here, maybe a dead tank circuit breaker whose tank is connected through leads to the ground grid. Anything that is electrically connected to the ground grid, that is bonded to the ground grid, is going to rise to the GPR. It's going to rise at the same potential as the ground grid is rising. So when this person in this picture is touching this grounded structure, he or she is functionally touching the ground grid, electrically touching the ground grid because it's bonded to the ground grid. So as the potential of the ground grid rises, there's a difference between this potential of the ground grid and the potential of the surface of the earth where a person's feet is located. And so that difference between the surface of the earth and the potential of a grounded object connected to the ground grid is touch potential. So that's touch and step potential. And fundamentally, ground grids are controlling touch and step potential so that they stay beneath levels that are determined to be safe for the application. So another thing that I've tossed around a lot, and it's going to be very important to what Rich is going to talk about, is split factor. Fault current division factor, which is commonly known as split factor, is the difference of total fault current that flows, percentage of total fault current, that flows through the grid to soil interface back to remote earth. Now, all the current has to go somewhere back to remote earth. If it's not going through the grid to soil interface, where on earth is it going? Well, that current is leaving through shield wires and neutrals that are for lines that enter the station and are connected to the ground grid when they enter the station. It leads through those shield wires and neutrals and then down those towers and in through those towers into the earth and back to the source. Split factor is going to be heavily affected by a couple of things. It's going to be affected by the number of line paths. And we say paths because if we have a double circuit line, that's where two circuits are sharing one tower, one set of towers, that only counts as one path leaving the station. It's going to be affected by the station's ground grid resistance. If the resistance between the ground grid and remote earth through the soil is very high, then by basic current division, that means that more current is going to go through the shield wires and neutrals down the towers. Another important factor is the resistance of towers, and we don't model split factor typically by putting the resistance of each tower into the split factor simulating program like WinIGS or CDEGS. We usually make broad assumptions. A typical low value might be 15 to 25 ohms for a transmission tower, individual transmission tower. The high value might be 1 to 200 ohms. So the value of the resistance of towers is a very important factor. And another factor is, are there any grids nearby? If there's a grid nearby, that's going to help the ground grid quite a bit, and that will lower your split factor. So let's look at a picture of split factor. Here we see a enhanced version of our previous picture where we showed a source providing ground current through a transmission network to a single line to ground fault in a station. And we see that some of the current is leaving the ground grid through that grid to soil interface, through the soil back to remote earth. Another portion of this current is traveling through the ground grid up through where the shield wire or distribution neutral is grounded, through the shield wire, back down each tower into the earth and back to remote earth. Now, I said that 15 ohms would be a very low value that we would assume for a transmission tower, and a typical value for a ground grid might be 1 ohm. So 15, 25 ohms, that may be a lot, but when you put dozens of towers almost in parallel, with aside from the small resistance of the shield wire, then that lowers quite a bit, and split factor can be quite significant. So this is a picture of split factor, and we see here I put in a picture of split factor with a neighboring ground grid nearby. I talked about how a typical very low value for grounding for transmission towers might be 15 to 25 ohms. Well, if you have a couple of spans of towers and then you enter the shield wire enters a 1 ohm ground grid, like we see right here, that can have a very significant impact on split factor as well. So the proximity of nearby ground grids is another significant factor that impacts split factor. So with that, hopefully I have given you enough information that you can appreciate some of the very significant ideas that my colleague Rich Keil is going to be presenting to us.
Thanks, Gerry. So we're going to talk about grounding renewables and presenting some of the challenges that take place when you have a situation where you have a number of different grounds located relatively close together. So what are some of these challenges? Well, what we need to know is that there is an interaction between grounding systems. And the grounding systems typically are connected through, as Gerry described, shield wires or neutrals, and those neutrals can be in cables or overhead conductors. But there's also conduction through the earth, which ties the grounding systems together. In the good old days, when I started in the utility industry, a utility owned the generation, the transmission lines, the transmission substations, the distribution substations, and all the distribution. So if you wanted to find out some information about the system, you just walk down the hallway and ask somebody. But unfortunately now there can be different owners that are involved with different parts of a collector, solar, and utility substation, which are all involved with getting the power back to the utility from either the solar plant or a wind plant. So one of the big problems is just trying to get information. And there's always seems like some reluctance to share information, even though it is really important to do a good grounding design, to have a lot of information. And a lot of that comes from the fact that there's a lack of knowledge about the interaction of ground electrodes. Okay, so what is the interaction between the electrodes? Well, if you got a utility substation, a collector substation, and a solar plant grounding system, and I'm going to use solar plants as the typical, and same thing holds true for a wind generation, but they're not islands. They're not separated completely from each other, because they have the physical conductions that I talked about, and also the conduction through the soil. The design of the grounding system needs to consider this interaction in order to make sure that you're designing it to the correct fault current that is available at the different sites. And you need to design the ground grid based on the fault that creates the highest or the maximum ground potential rise at the solar and the collector plants. So what causes the interaction? Well, when a voltage source is connected to a ground electrode that's buried in the earth, current flows into the electrode into the soil, as Gerry described. The earth acts as a resistance to that flow of current and creates potentials on the surface of the earth. if you connect the dots, if you take the magnitude of the potentials and you connect them together, then we end up with what we call equal potential lines. And that's, I say, is a voltage, but it's a voltage between equal potential lines. And when the electrodes are in proximity to each other, then they interact. So what's that look like? Well, if you take a ground rod and stick it in the ground and you energize the that single ground rod, then as you can see, the blue lines represent the equal potential lines, and those lines drop off the potential with respect to remote Earth. The smaller or lower on the outermost potential line, and the inner lines are higher than with a higher voltage, but than the outside. Okay, so each concentric circle represents a particular ground potential rise, and the further you get away from the ground rod, the lower the potential is. So this is what the voltage profile looks like for a one ground rod. And as you can see, the potential drops off fairly rapidly at the edge of the ground rod, and that will extend out until the voltage essentially goes to zero at remote Earth. What happens if you put two ground rods relatively close together? Well, as you can see, you energize both of the ground rods, and the equal potential lines are no longer nice concentric circles. On the outside, they kind of look like ovals, and inside, kind of like a figure eight. You can think of it as that. And when you look at the potential profile of those, you can see that the voltage does not drop off in between the rods like it does on the edges of the two ground rods. The same thing happens when you end up putting grounding systems together. So in order to come up with a good design, you need to know a lot of information. And this is where it goes back to the fact that you don't necessarily have all the information in one spot. But the model that we're going to discuss and show you how the different ground grids interact. I'm going to describe those on this slide, which is at the utility system. We got transmission lines coming in, and we can, if you can find out, you want to know the configuration, what the conductors are, how many lines there are, what the shield wires are made out of, what the pole grounds are. There's a lot of detailed information you want to find out. The transformer data in the example I'm going to have show you is 115 kV to 11 kV delta Y transformer. You need to know what the grounding information is at both the utility and the collector station, and the interconnection between the utility, collector, and solar plant. You need to know that. It's a transmission distribution line. In the case that I'm going to show you, the distribution line is 11 kV, three-phase overhead line with a neutral. The transformer data is a 11 kV to 425 volt delta Y, and the conductors connecting the solar and the collector substation together is a 15 kV 500 KCM copper. And what we want to do is try to determine what fault will cause the maximum ground potential rise at the collector. substation and the utility, or at the solar plant. So this is the WinIGS model that we're going to use to show the interaction between the different facilities. So you got two lines coming into a utility substation, and that utility substation has the 115 to 11 kV delta Y transformer. And what we're going to do is we're going to vary the distance of the distribution line from 2 miles to a quarter mile, which basically puts the two substations from 2 miles to a quarter mile apart. And then we have the collector station that has the 11 kV to 425 transformer in it.
For training that perhaps you might give more use elsewhere.
Big energy.
Dale, I think your mute just came off. 1 second.
Okay. So then we have the model of the solar plant, and you'll notice that there's different nodes that are around the drawing, and each one of those nodes is a place where we can determine what the voltage is with respect to remote earth or the ground potential rise. Okay, so we look at what the collector substation and the solar plant facilities look like. The solar plant is essentially a 2,000 foot by 1,830 foot footprint. There's lots of solar panels in this plant. You have 4 places where you have inverters, and they're described as DC 01 through 04. The collector station is a 200 by 200 foot ground grid, and it's located fence to fence approximately 750 foot apart. Those nodes are going to be important, and keep in mind where those are located. And the ones that I forgot to point out are the fence nodes. And this is to determine what the voltage is on the fence at those 2 corners. So what we're going to do is determine what happens when the maximum ground potential rise fault. The substation and the collector station are moved closer and closer together for that fault. And then we're also going to look at it when the substation is 143 feet apart and 10 feet apart, and the substations are connected together through their ground grid. Okay, so the ground potential rise that we're looking at is for a fault that actually occurs on the high side of the utility transformer. That is the fault that creates the maximum ground potential rise at both the collector station and the solar plant. So as you can see, the voltage when at the solar plant, when you're 2 miles apart, is approximately 410 volts. At 1 mile, that voltage increases to around 740 volts. At a half mile, it's closer to 1,070 volts. And a quarter mile apart, it's almost 1,300 volts. So if we look at that on a graph, for us folks that are more visual, you can see that as you move the solar or the utility closer to the collector station, there is an impact on the collector station, and the voltages basically go up in the solar plant from about 410 up to around 1300 volts. So if we look at it, what's happening with the fence, it follows the same trend. The closer you get the utility substation to the collector station, the GPR in the solar plant goes up. And so on the fence at 2 miles, it's at approximately 270 volts, and a quarter mile, it's up to about 850. So what's this have to do with the design? Well, if you are designing this and it's 2 miles away, it may be safe at the solar plant because the touch voltage may be below the tolerable. But if it's only if it's a quarter mile away, then the voltage is up to 855, and that may not be safe. So in one instance where it's 2 miles away, it could be safe, and if it was closer, it may not be. So again, for us visual folks, if you look at the graph, this shows that the voltage is going up from about 255 up to about 850. So what's the ground potential rise at the collector station and at the utility as you move the two substations closer together? Well, PV2 is the collector station and sub 3 is the ground grid at the utility. So if you can see that at the utility, it's the ground potential rise is approximately 8,600, and it's a little over 3,500 at the collector station. But if you move the utility closer to the collector station, as you can see, the voltage at the utility actually goes down, and at the collector station it goes up. And the closer you get the two together, you can see the results that when you get a half mile apart, all of a sudden the collector ground potential rise is higher than the utility substation. You get them really close together. The ground potential rise at the utility sub goes down, but it goes up higher at the collector station. Again, for us visual folks, if you want to look at it on a graphical, or on a graph, you can see that the ground potential rise goes down for the sub 3, and it goes up at the collector station. So that's the interaction that we're looking at. So with WinIGS, we can actually do two different types of faults. Okay, the first one is that you can put a fault at a particular one of those nodes, and you can ask it to tell you what the voltages will be for a fault at that particular node. Or you can ask what where the maximum ground potential, the fault which will cause the maximum ground potential rise at that particular site. So if you remember going back to the slide, PV1 was the high side of the collector station, PV2 was the low side. And this kind of goes back to what Gerry was talking about. The maximum ground potential rise, these numbers ought to look familiar because this is the numbers that we had on the previous slide that I had. And the earth current at the utility substation was about 2,500, and or the resistance, I'm sorry. And but the current is about 3450, and the voltage was just a little under 8600. Okay, so if you look at these voltages and compare them to a fault on the low side of the distribution transformer at the collector station, you can see that the fault current is much, much higher, about 3 times higher than it was for a fault at the utility. But as Gerry described, most of this current is flowing back through the ground grid itself and does not create a ground potential rise. And if you look at what's happening at the fault on the high side of the collector station, fault current is higher and the voltages are higher than they are on the low side, but they are much, much lower than they are for the maximum ground potential rise that happens at the utility substation. And if you move, that was at 2 miles, and if you move the substation, utility substation closer to the collector station, the same thing happens, except now the voltages are higher for the maximum fault. They're also higher for the distribution. And if you notice, the fault current went up a little bit higher on the low side of the transformer, but it still has minimal effect on the ground potential rise itself. And the same thing holds true if the fault is on the high side of the collector station. The fault current goes up, and it's actually higher than it is at the utility, but the voltages are not as high. So that really shows the interaction between the two. So now if we look at, we have to change the model slightly in WinIGS to put all 3 of the facilities in the model. Basically, it's the same model, except now we've got a ground connection between the all the utility and the collector and the solar plant. They're all tied together. And the nomenclature had to change a little bit. So the utility substation is now sub 5. That's the ground grid there. PV3 is the new name for the collector grid. These stay the same in the solar plant. So what happens when we look at the results when these ground grids are tied together and the distances are much closer together? Well, these when it was a quarter mile apart, these voltages were approximately 1300 volts, and these were a little closer to 1000. And so the closer you get them together, again, you can see that the voltages actually do go up some. And the other thing that changes is the split factor between those. The split factor on the other one was lower than that. I can look at that. The split factors are only like 13% here. But when you tie the ground grids all together, then that definitely changes the split factor. Okay, so what we have shown is that by changing the distance between the utility and the collector station, the voltages at the collector station and at the solar plant change dramatically. So what happens if we look at going back to the original and we have 200 or 2 miles between them, and we take the utility substation and instead of making it 160 foot by 160 foot, we change it to 620 feet by 620 feet. Well, as Gerry said earlier, the footprint of the ground grid has an impact on the resistance value. And as you can see, the resistance for the large utility grid is now 0.81 ohms as compared to the 2.5 ohms of the original. And so what does that do? Well, if you remember, these numbers again basically are the same that we saw earlier, but by making the utility substation larger, we have changed the voltages at the inverter and the defense and at the collector station. And the split factor changes pretty dramatically. It's almost double the split factor. So what does that do? That increases the fault current at the substation, and the voltage actually goes down because this is the current times the lower resistance value. So what we have done so far is show that there's many things that can actually change the impact between these substations. So kind of the conclusion we come to when we go through this process is to show that the grounding systems do interact and influence each other. And in order to do a good design and make a design that you can be comfortable with and eliminate a lot of the assumptions that you have to make, you have to understand the interaction between and how they influence each other. So the ground grid design needs to consider the interaction and determine the fault that produces the maximum ground potential rise at the utility and collector substations and at the power plant. And it may not be when somebody says, okay, I want you to design the collector station, and they don't want you to consider the fact that there's a utility sitting right next to it, 20 feet away, how that's going to impact it. And as you can see, there's a large impact of what the voltages are that are developed in the solar and in the collector station, just depending on how close the utility substation is to the collector substation. There's a lot of variables that can change this. As I showed you, the ground grid resistance going from 2.5 to 0.8 ohms made a big difference. If you change the pole grounds, that the resistance of those pole grounds will have an impact. The size of material you shield and the neutrals will have an impact. If you go from a steel shield wire to a aluminum carrier for a fiber optic, the resistance of that is typically much, much lower, and that'll also have an impact on the split factor and the interaction between them. The utility substation configuration, you put more lines in, you may have a higher fault current, but you also have more ground pass for the current to flow out. Transformer connections can change something, the impedance of the transformers. All of this has an impact on the interaction between the utility, the collector, and the solar or the wind plant. And so that's the whole point of this webinar, is to give people an idea that it's not as simple a problem as you might think because of this interaction between the three different entities. those facilities can vary tremendously. If you got a solar plant and you got thousands and thousands of poles supporting those solar panels, each one of those is basically a ground rod sticking in the ground. And that the resistance of that solar plant, the larger it gets, the lower the resistance is going to be. And that's going to have also an impact because the current is going to go wherever it can through the lowest resistance to get back to its source. So with that, we can move on to the question and answers. So Lake, I guess you'll take over.
Yeah. Thank you all. Appreciate that. Gerry, Rich, fantastic job. Really, really nice job breaking down such a complex issue and making it very digestible. So everybody feel free to ask your questions and put them in the Q&A section located towards the top of your screen. We'll get those started. And I can kick us off here while we wait for a couple of people. So Gerry and Rich, what are you guys want to put on mute real fast? Okay. What are some of the best practices for coordinating grounding design across multiple stakeholders, such as the utility company, potential developers, or the construction company?
Well, I guess the thing that we got to convince people is that we got to break down the barriers. We can't treat each one of these installations as a silo. And being able, I think that's probably the first thing that we have to do is we have to kind of educate the utility company and the developers of these programs or these facilities, maybe is a better word, that there is an interaction and there needs to be discussion between each one of those entities, and that the more information that is provided to the person who's doing the ground design, and the better they can model that, the more cost effective the ground grid can be. If you were designing a collector station and you thought, well, I got 40,000 amps, you're going to put a lot more conductor in the ground than if it's 20,000 or 5,000. So the more information you can give the designer, the better and the cheaper design most likely is going to come out of the process.
I'll throw in there as well is that it is important to put into your project plan and project schedule communication between the different entities from the beginning. Know that, because it's really the same thing that we find with data centers, actually, that we're doing a great deal of transmission substations that connect to a data center substation, or the other way around. A switching station connected to a step down station is just knowing that, hey, there's this grid nearby, and we're going to the project team is going to plan to have this design, a preliminary design done by this point, and we'll expect a preliminary design by this point. Just having that in the plan is very important and beneficial.
Fantastic. Thank you guys for those great answers. And we do have a couple of questions here. And Gerry and Rich, if you guys will mute until I ask the question, it'd be great. Perfect, thank you. So, does different grounding means and methods, as well as location of grounding the bus and different electrical equipment during outages, impact the split factor?
You want to read that again?
Yeah, definitely. Does different grounding means and methods, as well as location of grounding the bus and different electrical equipment during outages, impact the split factor?
Probably not so much. If I understand the question correctly, I think what they're really referring to is the connections between grounded equipment and the ground grid, and that will typically, yes, your leads will have a small impact on lowering your ground grid, and in reality, your foundations are going to help, are going to play a role in also lowering the resistance of your ground grid and assisting your ground grid. But typically, what we do is we don't consider them. They are it's a conservative assumption that helps us, and the leads themselves don't have a significant impact. So I would say that it's fairly minimal impact.
Yeah, and then the voltages, especially in larger substations, where you're standing in the substation or where the fault occurs in the substation, will have some impact. But by and large, the ground grid itself is not an equal potential plane in a large substation, because there is voltage drops through the conductors in the ground grid itself.
Fantastic. Thank you for that, guys. And here we have a question from our very own Jacob Knowles. So grounding studies are typically performed with resistivity measurements prior to any construction. How important is taking resistivity measurements after the new fill is constructed, and will that impact the study afterwards? So, fantastic question. I was wondering myself.
Well, that all depends. If you do a lot of grading and you change the topology of that area, it can have a tremendous impact. If you're basically starting with a flat surface and you're just pushing a little bit of dirt around and you're not going very deep, it's going to have very little impact on it. So it really depends on the situation. And that's one thing I always tell people in the tutorials I've done as chairman of the working group, is that one size does not fit all. You have to look at each individual substation and the surrounding portion of that substation in order to come up with a good design.
Lake, you're on mute.
Oh, sorry about that. I said this was from Dave Lewis, and he says he might have missed this in the very beginning, but was there a significant difference in the fence voltages and the solar panels or supports or inverters? And similarly, how much difference was there in the fence line voltage closest to the substation as opposed to the far side of the site?
Well, in this particular instance, there wasn't a whole lot of difference between the voltages on the fences at the two corners. There certainly can be major differences depending on the soil conditions. It could vary over a quarter mile or half mile for sure. But in this instance, there wasn't much. There was a big difference as you move from 2 miles down to 10 feet away. It went from about 270 up to over 1,000, if I remember the numbers correctly. But by and large, once you get the fence locations, it's a good idea to check the corners where the maximum touch and step voltages most likely are going to occur. So you need to check those at all four corners of your design.
All right, fantastic. Well, we only have about 30 seconds here left, so we'll thank you everybody for those great questions. We'll go to the next slide here and take a couple final notes. So again, I'd like to remind everybody that you are now eligible to receive a PDH credit. So feel free to send myself an email, lake.lund@cai-engr, and I'll place it in the chat right now. And you can also email our marketing team at marketing at the same domain. Our next webinar will be in August, and we're very excited for that one. More details to come here shortly. And if you guys want to take a look at this webinar recording or any of our prior webinars, definitely subscribe to our YouTube channel. And I just, again, want to thank you all for taking the time out of your busy schedules. Gerry and Rich, you guys did a fantastic job. And we look forward to progressing. And thank you all so much for taking the time. Give us a follow on LinkedIn as well. We typically post a lot of different projects that we've done. Fantastic stuff that has to do with Commonwealth. And we're so very proud to share our company with you. So thank you for joining us.
Thank you for joining us.
Thank you.